Hello anatomists and physiologists. This video is another video in our chapter 18 cardiovascular system series. This video is all about cardiophysiology, specifically the electrical events of cardiophysiology. So let's jump in. Part 2 of this video series talked about action potential. So let me highlight with my little marker here. Let's see, in dark green, where our action potentials exist. It exists from step 1 to step 3 here. So here's our action potential, all of that stuff in there. And then it will repeat again. Okay. So what we're looking at here is we have time, our membrane potential, our voltage there on the y-axis, and time here on the x, just like the membrane potential graphs we were looking at in Bio 430. There's three major steps to cardiac action potentials, and I'll highlight them for you as I go through. So the first step is the pacemaker potential. The pacemaker potential is done by pacemaker cells. So let me write that. So established by pacemaker cells. Pacemaker cells. These pacemaker cells spontaneously depolarize. The thing that's different about action potentials in skeletal muscles, which we learned about in Bio 430, and the action potentials of cardiac muscle cells, which we're talking about now, is action potentials happen not due to sodium, but more due to calcium. So that's a little bit different. So these pacemaker potentials, they happen because we still have potassium channels though. Potassium channels, if you remember from Bio 430, cause repolarization, making that cell more negative. So potassium channels make the cell more negative. So by closing those potassium channels, we're stopping repolarization. That's important. And stopping hyperpolarization afterwards, which is going below resting membrane potential hyperpolarization. We also open the potassium channels. So we still have potassium channels happening. So potassium channels, they open. So potassium channels open, and sodium channels open and potassium channels close. Both of those events lead to the cell getting more positive, more depolarized. But I think of pacemaker potential as like a pre-potential, a prep potential, because the cell is getting a little depolarized, but it won't really get depolarized until step 2. All right, so speaking of step 2 is actual depolarization. And this is actually when action potential begins. When action potential begins, the pacemaker potential has made its way up to the threshold. So here's our threshold potential here. That's the voltage at which action potentials can absolutely happen. And this is due to calcium. This is the thing that's due to calcium influx. So instead of sodium channels, as we learned in 430, in skeletal muscles, it's due to calcium. So that's the big difference. Otherwise, pretty much same. And then, of course, what goes up must come down. So we have our pre-potential and our pacemaker potential. We go up in the depolarization phase and then back down. And that going back down is coming back to resting membrane potential, which we know the definition of going back to resting membrane potential is repolarization. In repolarization, what happens is the stuff making our cell more positive closes, and that stuff is calcium. So when in doubt, the answer in cardio is calcium. So calcium channels close. That makes the cell become less positive, more negative. It also opens are potassium channels. So potassium channels, they open. Both of those events lead to the cell going in the downwards directions. That makes the cell less positive or more negative. Those are synonyms, right? Overall repolarization, so we come back down. So what does this look like in the heart cell, or in the heart cells? Our pacemaker cells, they have a special area that they like to live. Special areas, actually. The first area that our pacemaker cells like to live is this place called the SA node. The SA node, I'll write it to the side here. So I'll use a big marker to label this. That's the sinoatrial or SA node. A node is just like a group of stuff. So here it's a group of pacemaker cells. And it lives in the top of the right atrium, specifically the right atrium, really close to where the SVC, superior vena cava, kind of comes into that right atrium. And so sinoatrial refers to the atrium, but it's also where we get that word sinus rhythm. We'll come back to that, sinus rhythm. But there's also another place that our pacemaker cells like to live. This one's called the AV node, the atrioventricular node. Atrioventricular node, or the AV node. Atrioventricular because it's still in the right atrium, but it's close to the ventricle, so the AV node. So what happens is that the impulse, that depolarization, comes from the SA node, and the SA node sends that signal, sends that depolarization all around it, and that impulse will reach the AV node, which then does the same thing, spreads that impulse. All of the yellow things that we see here are how that impulse is carried throughout the heart. So the AV node carries that impulse down the middle of the heart and out, down the middle of the heart and out the other way. So it carries that impulse. So what we're looking at, this is called, so how that whole conduction happens is the intrinsic cardiac conduction system. So basically the power lines inside of the heart and how it works. So then the impulse, the original thing, comes from the SA node. That's this guy. Spreads it to the AV node, that guy. And then that impulse travels down these branches. Those branches are called the AV bundle or the bundle branches. They're also called the bundle of His. So I'll write some of these words down. So this guy, like if I were to like grab around it, those guys are called the bundle branches. Or we can call it the bundle of His. And that's a proper noun because it's some guy. Bundle of His. Okay. But then it travels to the rest of the heart. And if you think about nerve impulses, if you think about action potentials, we talk often about this wave of depolarization. So how that happens is it goes up and down and up and down and up and down and up and down, and it passes, that wave of depolarization goes up and down, and that wave travels. And that's kind of how I think about this intrinsic conduction system, is that impulse travels down the heart, into the walls, all the things. The last part of, so from the SA node, we travel to the AV node, we go down through the bundle branches or the bundle of His, and then we go to all these fibers. You see how these are so much smaller. Those have a special name, those little fibers are called Purkinje fibers. And there's a long name for it. I'm going to highlight it for you in red. So all those little fibers are called the subendocardial conducting network, or Purkinje fibers, which personally, that's the name that I like better just because it's shorter. Named after some person, Purkinje, okay? So those Purkinje fibers are how we spread to every single last cell. This is really great how our intrinsic conduction system is organized, because if you think about it, first what happens is our atria fill. We pass all that blood into the ventricles, and then we need to push that ventricular blood to the next vessels. It needs to go up. Wouldn't it make so much perfect sense if the ventricles contracted first from the bottom at the apex, and then contracted last at the top near that atrial ventricular septum? And that's exactly what happens because of this intrinsic conduction system, because our impulse travels down to the apex first and then up. That's exactly what happens. Isn't that so cool? Okay. And we'll talk about what happens when this conduction system doesn't work properly, but that's a future video as problem. Okay, so the SA node has its own rhythm. The SA node has its own rhythm. The thing is that we have innervation coming into the heart too. And so that's our next slide here. Our next slide is that while we have pacemaker cells, while we have all this other great stuff, the heart has innervation from two main things. So I'm going to write in my notes, the heart is innervated by the ANS, autonomic nervous system. First, we have the SNS, sympathetic nervous system. That's an excitatory thing. So the SNS leads to increasing the rate and the force of contraction. But we also have the PSNS, parasympathetic nervous system, by way of this guy, vagus nerve. If you remember from Bio 430, vagus nerve is the parasympathetic nerve that we'll talk about forever. So when in doubt, if it's parasympathetic innervation, you're guessing it's probably the vagus nerve. But the parasympathetic nervous system has a calming effect, a relaxing effect, a slowing effect on the cardiovascular system. So this leads to the parasympathetic nervous system, the vagus nerve, leads to a reduction in heart rate, beats slower. So that's in addition to our SA node, our AV node, doing their own thing on their own time. There's additional innervation to it on top of it. We'll circle back to this. Okay, so action potential. There's a couple of things going on here. There's two major colors. The two major colors is we have dark blue and we have purple. So the dark blue, that line refers to our action potential of cardiac muscle cells. The purple, that's tension. Tension. So what I want you to notice here is that while we have depolarization, the cell getting more positive, notice that the muscle cells aren't actually contracting, aren't really creating tension until like a little while later. Notice there's time in between there. Do you see that time difference? So what I want you to get from this is that the electrical events, the action potential events precede, action potentials events precede the mechanical events, the contraction, precede contraction or relaxation. So notice that we go up, depolarize. You'd expect with depolarization we'd have contraction right away. We do, but a couple of milliseconds later. On repolarization, you'd expect we'd start to relax. We do, but a couple of milliseconds later. See what I mean? So those electrical events, the action potential stuff, comes before that contraction relaxation bit. Keep that in your brain. We're going to come back to it. Okay. So cardiac muscle contracts because of electrical activity in the form of action potentials. That's the electrical activity of the heart. And just so you know, we're going to circle back one slide. What I wanted to tell you about on this slide is that, do you remember in skeletal muscles when we're talking about how you can have a stronger muscle contraction? Like if you need to lift a heavier weight, you can, because we have summation. Because sending those nerve impulses leads to a stronger contraction. We don't really have that in the heart, not so much, because this absolute refractory period is such that we can't really summate our action potentials. Not really, so we don't really get that. We can get faster or slower, or we can increase ever so slightly a little bit, but not to the extent that we do in skeletal muscle cells. So that's something really important to think about. Not that I need you to recite the absolute refractory period is such that I just want you to know that it's really important that the heart can't really contract more strongly like we saw in 430 with skeletal muscles, because we want the heart to fill fully with blood each time it beats. We want it to work effectively. Okay, back to this. So electrical activity of the heart is action potential. We can read what's happening at the electrical level of the heart using electrical methods. Electrocardiography, or ECG, which is just a graphical representation of that electrical activity in the heart. It's not one action potential, it's like a combination, a composite of action potentials in any given subject, right? And so just keep in mind, whenever we're looking at ECG, whenever we're looking at any graphs for cardio, I want you to remember this part. Electrical events cause mechanical events. Depolarization causes contraction. Repolarization causes relaxation, okay? So think of those as causes, so there's a little bit of a delay. It's coming. Okay, so here is what an ECG might look like. Notice that we have all of these little leads, these little readers that are reading the electrical activity. They're called electrodes. And we'll get to do this in class, a little bit more simplified version that we have available to use for us. You can take ECG on the torso and the thoracic cavity and a little bit into the abdominal cavity, but we can also use the limbs, and that's what we'll do when we're in the lab. All right, so what does an ECG look like? It looks like this. So ECGs have this typical kind of look where it kind of is flat, and then it goes up, and then it goes down. Oops. We go like this, and then we go down, up, and then we have another little loopy there. I'm drawing this here because you might have seen this before. Like there's lots of like healthcare worker logos and things that kind of have an ECG kind of look. And it's because it's really important in healthcare, right? So each of these waves has a name. The first little hump is called the P wave. The zigzaggy part is called the QRS complex. And the last wave is called the T wave. Okay, so what I just drew here is a very simplified version of all of that. Okay, and each, if you're wondering, the QRS complex is actually Q, R, and S like that, but we don't really care. We'll call it QRS altogether. Each of these waves means something is happening electrically, because our flat line here is no electrical activity. But then when we move, we deviate away from that line. That means electrical activity is happening inside of the heart. So if we were to look at an ECG, we'd see these, hopefully in a normal ECG. We'd see the P wave. The P wave corresponds to when we have the SA node, that's the group of pacemaker cells sitting in the top of the right atrium, when they depolarize. So the P wave is atrial depolarization. And notice that this graph has that labeled for you. Atrial depolarization, that's the P wave. Once the SA node is depolarized, that passes its signal to the AV node. And then the AV node passes its signal in between the ventricles and up the side of the walls, leading to ventricular contraction, right? And so that's exactly what happens. So the QRS complex is ventricular depolarization. I'll circle that. Ventricular depolarization is the QRS complex. Remember that when the ventricles depolarize, that leads to the ventricles contracting because electrical events cause mechanical events. Mechanical meaning like the actual moving of the thing. All right, and then the last step is the T wave. The T wave is when the ventricles repolarize. The ventricles repolarize because, well, we go up and then we have to come back down because that's how action potentials work, right? When ventricles repolarize, ventricles relax, but like delayed because electrical events cause mechanical events. So that's a typical ECG, okay? But wait, there's more. There is more to discuss. Okay, so next thing. So we have the PR interval. What that means is what we're looking at is this segment here. So from the start of the P wave to the end of that P wave right before the QRS complex, that PR interval is when the atria get excited. When the atria get excited, that causes the ventricles to get excited. When the atria get excited, the ventricles get excited because that's how the conduction system works. The AV node, and then we pass to the interventricular septum and then pass up the ventricles. That just means that we've really ignited this whole intrinsic conduction system. That's the PR interval. We also have the ST segment. The ST segment is the end of that QRS complex to the start of the T. That little flat part there. When the cardiac muscle cells are about to contract, they're kind of like all depolarized. That's the ST segment. The point where all of those cardiac muscle cells are depolarized, which means they're all starting to contract. Okay, so that's normal ECG. We're going to talk about this more in the classroom because we get to do some labs on this as well. But that's like a future S problem. Okay, so circling now to our next slide. There's a lot of things going on here, but I'm going to zoom in on each of them. What I want you to keep in your brain is electrical events lead to mechanical events. Electrical events cause mechanical events. So even though we have the SA node that's depolarizing, that's an electrical event, that will lead to contraction. Does that make sense? And if you look in your text, there's a really great video that talks about each of these segments. Okay, so again, first what happens is we have the P wave. And the P wave, that's when the atria depolarize because the SA node's doing its thing. That means releasing its signal of depolarization. So that's P wave. The SA node spreads its whole signals to the AV node. That's the little flat part there. The QRS complex happens when we go from the AV node down the ventricles to the apex. That's the QRS complex. When all of the ventricles, when all of those cells are depolarized, that's this little flat ST segment. When the ventricles repolarize, that's T wave. The ventricles, notice they're starting to repolarize. That orange is going away and replaced by normal red. That's starting to relax, starting to repolarize. And when ventricular repolarization is complete, then we're fully back to where we started. So depolarization, cell gets more positive. Repolarization, cell gets more negative. And even more when we talk about it in class. Okay. But ECGs aren't always normal. What I hope you see when you look at ECGs is normal, okay? Normal sinus rhythm, that rhythm initiated by the SA node. We'd see our P wave, our QRS complex, I should write our P wave, QRS complex, our T wave. We should see that. That would be normal tracing of our ECG. If we have some abnormal rhythms, here's some examples. We could have a junctional rhythm when the SA node doesn't really work properly. If the SA node in the heart doesn't work properly, remember we have a heart here, we have our 4 chambers. If our SA node lives way up here and it can't pass its signals, like that just doesn't work, then we have to start then at the AV node, and that's where everything starts. So our heart rhythm is going to be different. The AV node and the SA node each have their own rhythms. So if left alone, the SA node, I'll write it at the top here, SA node, that sits happy at like 75 beats per minute. So if the SA node is in charge, which it normally is, about 75 beats per minute, that's where we're at. If the AV node was only in charge, we'd be a little bit slower. The AV node, we would sit happy at like 40 to 60 beats per minute. So those are really big differences. That makes a really big difference in transport throughout the body for your blood, right? Okay, so that's junctional rhythm if your SA node doesn't work. We could also talk about heart block. Heart block is when your AV node doesn't work. When your SA node is firing, but the AV node is just not carrying that signal effectively. So what happens is the P wave still occurs because the P wave happens because of SA node. SA node works just fine.